from Signals and Systems given in GATE 1997 from the relation between power spectral density and autocorrelation function. Here it is given that the power spectral density of a deterministic signal is given by sin f by f, where f is the frequency. Then the autocorrelation function of the signal in time domain is. So here given the options: rectangular pulse, a delta function, a sine pulse, and a triangular pulse. Now we will see the solution for this. So here given that the power spectral density is given as T of the deterministic signal is given as a sin f by f is given. So we need to find the autocorrelation function from this power spectral density. We know the relation between the power spectral density and the autocorrelation function by applying the Fourier transform for the autocorrelation function. Fourier transform of the autocorrelation function is always equals to power spectral density. That's what we know. So using that concept here, power spectral density. So here what is given? The power spectral density is given. That is nothing but the Fourier transform of autocorrelation function is given. That is equals to sin f by f is given. So given that the Fourier transform of autocorrelation function are, let us consider x of tau is given as sin f by f. Now we need to get the rx of tau in time domain. Then we simply apply the inverse Fourier transform of sin f by f gives the autocorrelation function rx of tau here. So here, in order to find the inverse Fourier transform, we know that the Fourier transform of some rectangular pulse, taken as having the pulse width of minus tau by 2 to tau by 2, having an amplitude of a. So by applying the Fourier transform for this, we will get it as a tau into sinc of omega tau by 2. So here by observing that we got this as a sin f by f form. Sin f by f is nothing but that is the sinc function. So we need to have the inverse Fourier transform of the sinc function here. So we need to have the inverse Fourier transform of sinc function. Inverse Fourier transform of sin f by f we need. That is nothing but inverse Fourier transform of this is nothing but sinc function only. So we can say that the Fourier transform of this rectangular pulse represented with pi of t by tau is a tau into sinc of omega tau by 2. Then the inverse Fourier transform of this sinc function is equals to the rectangular pulse. Then we can say that rx of tau is must be equals to some rectangular. No need of some expression. Here we need to say whether the function is rectangular, square, or triangular pulse. So this is the rectangular pulse only in time domain. That's what the given options. So we can say that the answer is the rectangular pulse for this.